Now that we have gone over last class solids and kind of their properties based upon, is it a covalent solid, is it a metallic solid, ionic, or a molecular solid. We've gone over some properties of liquids and the intermolecular forces that hold them together. We have to go over those phase changes from going from one to another. So I like this diagram that should remind you from Chem 1 of our heating cooling curves. So solid on the left, gas on the right. I even like how they show the solid as a nice, neat structure, that lattice structure that holds it together. Liquids have a flow about them, gases aren't even connected, and it gives you, on the plateaus, the phase changes that are occurring between those. Those plateaus are where you're both solid and liquid on the first plateau, or both liquid and gas on the second. You're transitioning from one to another. But at certain temperatures, certain objects can be both one thing or another. You can have liquid water at 0 degrees Celsius. You can have solid water at 0 degrees Celsius. You can have liquid water at 100 degrees Celsius. You can have gaseous water at 100 degrees Celsius. So the term equilibrium is kind of referring to where those two states can coexist. My next slide here is talking about that transition from solid to liquid. Recall that that's called the heat of fusion. So energy required to break apart the intermolecular forces, that lattice structure, that nice organized manner that the solids will be arranged in. Because when you're a liquid, they're still held together, but there's a flow. So they're not held together as tightly. And I like to use the analogy of you guys right now are in a solid structure. You are in a specific spot. Yeah, you're vibrating about a little bit because particles are always moving around a little bit. But we're in a fixed position. But when we say, okay, here's what you're working on today, go ahead, there's movement around. So we have more of a flow about us, but we're all still contained. When that bell rings in 10 minutes and you all disperse all over the place, we are definitely in the gaseous phase now. Because we are nowhere near each other. I can't hold you in at all. So solid to liquid would be, okay, done lecturing, now we'll work on stuff, guys. You kind of move about in this area. Remember, melting is endothermic. You have to put heat in to make that happen. And if we look at that other phase change, liquid to gas, again, that the bell is going to ring in a little bit. What's going to happen is when you go from a liquid to gas, that heat of vaporization is even bigger. Because my last bullet point tries to bring this up, there is no more attraction at all holding things together. So when you go from a solid to a liquid, there's still some attraction holding things together. But when you go from a liquid to gas, you are getting rid of all attractive forces. So that's what heat of vaporization is referring to. Numerically, heat of vaporization values are larger than heat of fusion values for that reason. Heat of fusion is loosening it up. Heat of vaporization is just making it go. And I like this example of going over that phase change of liquid to gas. Because what this introduces is how pressure plays a role in state of matter. In Chem 1, actually, back in 8th grade, maybe when you talked about changes in state of matter, you focused on one thing, temperature. You heat things up, they can turn into a liquid, into a gas. I mean, that ignores the fact that we're breathing in gas right now, but again, in 8th grade, they had to simplify. In Chem 1, we simplified. We said it's not only the temperature that determines state of matter, it's the intermolecular forces. Things that are held together really well, they're a solid. Things that are held together a little bit, a liquid. Things that can't be held together really well at a given temperature are a gas. Pressure plays a role as well. Now, I've never tried to boil water at Mount Everest, and if you guys want to do a GoFundMe or some sort of bake sale to raise enough money for us to do a class field trip to prove this, we can. Or we could just go to like Colorado and show it as well. Because if you ever go to high altitude areas, they have different cooking directions at times based upon pressure. When you think of boiling, looking at this picture on the right-hand side, what happens when a liquid boils is the bubbles come up and then, they're gone. Well, if I have a great enough push down, it's going to be hard for that bubble to escape. But if I have a lower push down, it's easier for that bubble to escape. And that's why at normal sea level, water boils at 100 degrees Celsius. There's a fair amount of pressure pushing down on the surface of that liquid. Again, surface tension. But if there's less pressure pushing down, it's easier for the bubbles to escape. What we have to make sure that we understand in AP chemistry is not only is it temperature, not only is it intermolecular forces, but pressure plays a role in it as well. And I'm going to go over one more example of that in a couple of slides. Here is a table again that you flip to the back side of your handout. It's just reminding you of intermolecular forces and some of these properties. Now, the boiling points on the far right-hand side are at 1 atmosphere, because that is something that we would have to indicate. A lot of times students, when they read a story problem from AP Chemistry, there's a lot of data in it, and some of that data isn't even needed for your calculation. It's very common that they'll give you a value and they'll say, this is at 1 atmosphere. Just because we know water boils at different temperatures based upon the pressure. So again, reminder of things that we've covered a little bit today. CH4 is nonpolar. Again, when you see carbon-hydrogen bonds, nonpolar. C6H6, that's actually benzene. That's that ring that I showed you with the every other double bond that's not really every other double bond. That's also nonpolar. So they both have dispersion forces. However, benzene is larger than methane, which is CH4. That CH4, by the way, is what comes out of our gas jets when we light our Bunsen burners. Bigger nonpolars have more dispersion forces, which means they're held together tighter. That leads to a higher heat of vaporization and a higher boiling point. Water, on the other hand, hydrogen bonding. It's a polar covalent molecule. Sometimes it's reported as 40.79 kilojoules per mole. I just rounded off to the 10th place for this table here instead, and you can see the boiling point there as well. Keep in mind, however, if you had a big enough nonpolar, it could actually surpass a polar molecule in how well it's held together. It could surpass a polar molecule in its boiling point. Because if there's enough dispersion forces, there is a really huge attraction. I'm not going to do the phase change calculation right now. Maybe I'll start next class reminding you how we did that math in Chem 1. It's something that may or may not pop up. I want to end with these graphs instead. Because these graphs go back to state of matter and how it's not just temperature, it's also pressure that determines this. So when you look at both of these graphs, the x-axis is temperature, the y-axis is pressure. They're often referred to as triple point graphs. Because if you look at the graph on the left, there is a region where it's likely to be a solid, a liquid, and a gas. And there is always going to be that one point, that sweet spot where the temperature and the pressure allow all three states of matter to coexist. Solids typically are ones that are going to be at lower temperatures. So when reading the graph, I know that's going to be on the left-hand side. And usually they're going to be at higher pressures. Because if you squeeze it together, you allow those forces to work. Gases, on the other hand, are typically going to be at high temperatures. They're moving really fast. And they're more likely to exist at low pressures. Look at the bottom of the graph. You could have a gas at a really low temperature if it was a low pressure. Because if it's a low pressure, you're not pushing them together. So now you're not allowing the forces of attraction to take part with one another. So these graphs are really good at demonstrating that idea that it's not just temperature, but pressure also plays a role in state of matter. And again, intermolecular forces varies as well. The one thing I bring up that's kind of unusual about this is the graph on the left is slightly sloping left. The graph on the right is definitely sloping to the right. Water is what this one is for on the left-hand side. Water is one of the very few states of matter that at a higher pressure, the liquid phase actually becomes a little bit more favorable. Because water is more dense as a liquid than it is as a solid. Right before our winter break, we're actually going to show you a little lab activity that demonstrates how that works. This is probably for any other substance, really, because water is pretty unique in that. So, again, a quick little rattling off of notes, but the point was to tie together what we've been going over with the states of matter, solids, and liquids. I mean, we've already covered gas behavior in previous units. But then the change between them and how pressure, temperature, and intermolecular forces all play a role in that. Again, the web assignment that's due next time is actually from last class's lattice energy, but I did open up the intermolecular forces as well if you wanted to get that one done.